Okay, everybody, we still have another topic in Module 7 to finish, and then we will be finished with that, and then we can move on to Module 8, which covers gas laws. So what we are going to address today in this lecture is our oxidation and reduction reactions. So let's get started. Okay, so oxidation reduction reactions, or redox, are processes where we have the transfer of one or more electrons between reaction partners. So this is usually between atoms, between molecules, or between ions. So for example, this is magnesium metal. So this is in its elemental state. And then this is a nonpolar acid, or is a polar acid, where this is partially positive and this is partially negative. And when we look at this change here, now magnesium is in its ionic form, which has a +2 charge. So in my elemental form, that doesn't have a charge, so that's 0 state. And then my magnesium chloride has a +2 charge. So to get from 0 to +2, you had to actually lose electrons to do that, right? Now I have in my magnesium +2, I have more protons than electrons, and that's how I become positive charge. This actually went from a basically +1 because of this partial positive, it's very polar bond. And my hydrogen is the elemental diatomic form of hydrogen. So again, that's neutral. So I went from a +1 to a 0, where I lost an electron. Where I gained an electron, sorry. Because if I become positive, right, and then I become neutral, I went from a +1 to a 0. So that's a +(-1). So I gained an electron, and this would be part of this oxidation reduction process. When I lose electrons, that is undergoing oxidation. When I gain electrons, that process is reduction, and we're going to talk about that a lot. But the basic idea is that I have this transfer of electrons that's occurring. So, oxidation is the loss of one or more electrons by a substance, whether that substance is an element, a compound, or an ion. Reduction is the gain of one or more electrons by a substance. Now, this must happen together. So anytime I have oxidation, I have to have reduction. So I have these two processes going on. So the whole thing is called an oxidation reduction reaction, or more commonly, because chemists are inherently lazy, redox. So many times redox reactions involve the reaction of a substance with oxygen. So notice here, iron metal is reacting with oxygen. Now remember, oxygen is in its elemental state, and iron is in its elemental state. So these both have 0 charges. But here, my O is -2 and my iron is +3. So the iron went from iron 0 to iron +3 by losing electrons. And then the oxygen went from 0 to -2 by gaining electrons. So this was oxidized, this was reduced. And you can tell anytime I have these types of reactions with oxygen, I'm actually going to get this transfer of electrons, which means they are redox reactions. Combustion is a redox reaction. In this example of a combustion, remember, combustion is the burning in the presence of oxygen. I have hydrogen, which is elemental hydrogen, reacting with elemental oxygen, and what I'm forming is gaseous water. Now, again, this is going to be 0 states, and when I look at my water, my oxygen is going to be -2, and each one of those hydrogens will count for a +1. So what I get is hydrogen went to +1, it lost an electron, and oxygen went to -2, right? So this lost electrons, this gained electrons. This is my oxidation, this is my reduction, and this is a process of knowing what kind of numbers that I'm going to use in order to track the electrons, which I will actually talk to you more about later. But you can see here that I have hydrogen gas reacting with oxygen gas, and what I'm going to get is 2 molecules of H2O, and that would be considered redox because of those changes in oxidation numbers that above. Now, I don't have to have combustion. I don't have to have the presence of oxygen. This is metallic elemental sodium, which is also neutral. And this is elemental chlorine, which is neutral. Here I formed an ionic compound where my sodium is +1 charge and my chlorine is -1. So sodium went from 0 to +1. So sodium actually lost 1 electron. And chlorine went from 0 to -1. So chlorine actually gained 1 electron. So sodium was oxidized because it lost, and the chlorine was reduced because it gained. So here I can see that I get this transfer of electrons because I take my sodium solid, my metallic elemental form of sodium, and my chlorine gas, which is my diatomic elemental molecular form of chlorine, and now I'm forming this ion compound. And to make these charges, I had to transfer electrons. Here's another example, and you will see a lot of these where the full compound is not necessarily described, but the ions are. So here I have permanganate reacting with iron 2 and 8 protons. And what I get is manganese 2 plus iron 3 and then water. Now, the changes, manganese, what is the ion charge of manganese? Well, each oxygen is -2 and there's 4. I have a negative charge here, so this goes from +7 to +2. So manganese actually went from +7 to +2. It became less negative or less positive, so it gained electrons and it was reduced. And then iron went from +2 2 plus 3, so it became more positive. So it lost an electron and was oxidized. Hydrogen actually has no change. It's a +1 in both. So hydrogen is unchanged and oxygen is also unchanged. Hydrogen is a +1 before and after, and oxygen is a -2 before and after. So the change happened, the exchange of electrons happened between manganese and iron. So many of the times that we're discussing redox, we're going to have to figure out where my electrons are going. Where do they start? Where do they end? And a lot of times when I react metals with nonmetals, I'm going to have this oxidative redox process. So let's look at these, right? Elemental sodium, metallic is 0. Diatomic elemental oxygen, diatomic elemental chlorine is 0. My sodium is +1, my oxygen is -2. My sodium is +1, my oxygen is -1. All of these are examples where reactions involve a metal reacting with a nonmetal, and they both involve the conversion of free elements into ions. Sodium element goes to sodium +1. Oxygen elemental molecular species goes from 0 to -2. Chlorine molecular elemental species, diatomic, goes to 0 to -1. So basically, I have sodium losing an electron and oxygen gaining an electron. In the bottom reaction, I have sodium losing an electron and chlorine gaining that electron. So I do have this redox process that's occurring. And one of the things you want to look at is this conversion of free elements into ions. That's the type of situation that will distinguish these redox from other reactions that we've actually discussed. When we looked at precipitation reactions, the charges on the ions did not change. When I looked at acid-base reactions, the charges on the ions did not change. Nothing was oxidized, nothing was reduced. But in these types of reactions here, where I go from free elements, 0 charge, into ions, which either are cations and positively charged or anions that are negatively charged, I do have that transfer of electrons. Now, notice that my electron transfer does not need to be complete transfer for this to qualify as an oxidation reduction reaction. Here, I have a nonpolar diatomic molecular element hydrogen, and I have a nonpolar molecular diatomic element chlorine. And what I end up with is 2 HCl's. Well, this is a polar substance. My H is actually acting more like a +1, and my chlorine as a -1. But these are really partial charges where the electron density is over here pulled towards that more electronegative chlorine atom. So there is an uneven sharing of electrons when hydrogen bonds to chlorine. I have an increase in electron density, which also counts as reduction for chlorine, and a decrease in electron density, which will also be counted as oxidation for hydrogen. So these partial charges in these molecular substances also will fit this definition of electron transfer, and this type of reaction is still classified as a redox reaction. To convert a free element into an ion, that atom must gain or lose electrons. This process has to happen together. So if one atom loses electrons, another atom must accept them. So reactions where these electrons are transferred from one atom to another atom are classified as redox reactions. Atoms that lose electrons are being oxidized, and atoms that gain electrons are being reduced. So in this example, sodium goes from a 0 state to a +1. I lose an electron, that would be oxidation. Here I have elemental chlorine actually adding 2 electrons, because what I'm making to split that Cl2 is 2 negatively charged ions. But the important part is I'm adding electrons, so that's reduction. This is sometimes very simple, because when I look at metals and nonmetals that don't involve O2, or that do involve O2, I need a method to determine how the electrons are transferred. Again, sometimes it's very clear cut. I have free elements going to ions. Other times it's not that clear cut, like when I have my HCl example. So in order to determine how electrons are transferred, we use something called an oxidation state for every atom or element that is in a reaction. By looking for changes in these oxidation state, I can actually determine electron flow in the reactions. Now, you're going to notice that a lot of these oxidation states are going to look like ion charges, but they are not ion charges. My oxidation states are basically imaginary, and they're assigned based on a set of rules which allows us to do like a bookkeeping method in order to figure out where electrons are originating and ending up, which can allow me to track the reduction and oxidation processes if there is one. Don't forget, ion charges are actually real and measurable. Typically that unit is a coulomb, and I can experimentally determine the charges on ions. So don't forget that there is a difference. So I have some rules on how to figure out what the oxidation state or the oxidation number of for a particular atom. So this oxidation number or state is a value that indicates whether something is neutral, electron rich, or electron poor. So what I want to be able to do is look at these formulas and figure out, do I have a 0 charge, do I have a negative charge, or do I have a positive charge? And then I can track where the electrons are going if I have an oxidation reduction reaction. So let's look at how I assign these. An atom in its elemental state has an oxidation number of 0. I've referred to this several times when we've talked in these slides leading up to this one. Any metal that's just its pure metallic form is 0 state. Any diatomic element that is found as a diatomic molecular element is going to be in its 0 state. Any other element that I see on the periodic table that is by itself in its elemental form, the oxidation number is always going to be 0. Okay, rule 2. If I have an atom that is a monatomic ion in my compound, the oxidation number is identical to its charge. So sodium plus 1 ion, sodium ion, has an oxidation number of +1. Calcium has an oxidation number of +2. Aluminum iron has an oxidation number of +3. Chloride or fluoride or bromide or any of those halide ions have oxidation numbers of -1. Oxygen is always a -2. Well, always is a strong word. We're going to see an exception to that. Oxygen is almost always -2 in an ionic compound, or when I see oxygen, actually. So, an atom in a polyatomic ion or in a molecular compound will usually have the same oxidation number as if it would have if it were a monatomic ion. So hydrogen can actually be a +1 or a -1. When hydrogen is in hydroxide, which is OH-, hydrogen itself is going to be +1 here because my oxygen is -2. The sum of those oxidation numbers has to equal the ion charge. So +1 plus a -2 is equal to a -1. This is calcium hydride, and this is CaH2. Notice calcium always forms a +2. So in this case, hydrogen actually has to be -1. This is a neutral compound. So the sum of the oxidation states within the atoms that make up the compound has to equal 0. And if you add these up, I do in fact get 0. Here's my rule for oxygen. It almost always has an oxidation number of -2. There is an exception, and this is called a peroxide, where I have an oxygen-oxygen bond. This is a peroxide, where I have something O, O, something. In this case, only when my oxygen is forming a peroxide does my oxygen have a -1 as an oxidation number. Again, these are neutral molecules, so they have to, the oxidation states have to sum up to 0, and they do. But remember, peroxides. So this oxygen-oxygen bond is what you're looking for when you have a peroxide. Otherwise, it's always -2 for oxygen. Rule number 3. The atom in a polyatomic ion or a molecular compound usually has the same oxidation number as if it would have if it were a monatomic ion. This is the continuation. I just wanted to repeat that. And then look at halogens. Usually my halogens will be a -1, but there are cases where my halogens have much different oxidation numbers. These rules are in order of priority, so you kind of go down the list when you're trying to figure out these oxidation numbers. So in this case, if chlorine is a -1, hydrogen is a +1. In this case, I know that oxygen is a -2. That doesn't change. This is not a peroxide. because the rule for oxygen comes above the rule for chlorine, I have to understand here that in this OCl2 molecule, my oxidation state is not -1, it's +1, because the oxygen has to be a -2. So this has to equal 0, which gives me an oxidation number of +1 for chlorine. So chlorine and other halogens can vary widely, especially when I get into group 3 and 4 and 5, because remember, I have d orbitals and they can do different things. Let's look at rule 4, which I have alluded to throughout this rule discussion. The sum of the oxidation numbers has to be 0 for a neutral compound and is equal to the net charge for a polyatomic ion. So for example, if I wanted to figure out what that sulfur was, I am going to say, okay, well, hydrogen is +1, and we know this is an acid, and we know that the characteristic part of an acid is that it gives off a proton. Now, remember, some of these things I need to look at patterns, and I can recall prior information in order to help this become clearer. So then I know that each one of those oxygen atoms is a -2, and I have 4 of them. So I have +2 plus X plus a -8 has to equal to 0. So when I solve for X, I find that my sulfur is a +6 in terms of its oxidation number. Let's look at what the chromium is in my dichromate ion. So this is dichromate. It's a -2 charge. So whatever this is, the sum of those oxidation numbers has to equal to 0. By knowing that, I can figure out what the oxidation number of chromium is. I know oxygen is a -2. Again, this is not a peroxide, so oxygen is -2. And now I know I have 2 chromium atoms that spreads out whatever positive charge I need. So this is a -14. The net charge on the whole ion is going to be -2. So this charge has to be 2 times a +6. So what I'm going to have is 12 plus a -14 is equal to a -14. So my chromium, each one of those chromiums, and I have 2 chromium atoms, each one will have an oxidation number of +6. The 5th rule, in their compounds, nonmetals have oxidation states according to the table below. Nonmetals that are higher on the table take priority. So this will vary, and I'm going to go in priority based on this table. So fluorine is usually a -1. Hydrogen is usually a +1. Oxygen is -2. Group 7A is -1. Group 6A is -2. Group 5A is -3. Those are all pretty predictable. If you were going to look at ions that form from these various atoms, you would predict these charges. The problem is, well, maybe not for hydrogen because it's in 1A, but the problem is these are nonmetals, and generally they're going to form either ions or covalently bonded compounds. So you want to use these rules in order to help you assess what charges, what oxidation states these nonmetals have. So let's look at this. I want to assign oxidation numbers to each element in the final in these compounds. So if I look at SO2, I know that oxygen is a -2. There's no peroxide here. This is a molecular compound, sulfur dioxide. Oxygen is a -2. So whatever sulfur is plus a 2 times a -2 has to equal 0 because it is going to be a neutral compound. It's not an ion. So my sulfur needs to be +4. Let's look at this. This is chromate. I know that my oxygen is a -2, so let's figure out what the chromium is. There's only one chromium, so I know that +4 times -2 has to equal the ion charge, because there is one. So what do I get? I get something plus -8 is equal to -2. So my chromium is going to be +6. Again, my oxygen is going to be -2. With ammonia, we just talked about that. Nitrogen generally forms a -3, and hydrogen is a +1. So my nitrogen is going to be -3. My hydrogen, right, is going to be +1, and I have 3 of them. So that gives me 0. So I know nitrogen is a -3, hydrogen equals a +1. And then when I look at the charge balance, I can tell that that's correct. Now this is chlorate, ClO3 minus. I have chlorine plus 3 times -2. I know my oxygen is -2. And this has an ion charge, so that has to be a -1. So something plus -6 equals -1. So my chlorine is going to be a +5. See, I told you they do weird things. And then oxygen is going to be my -2. SF6, well, my fluorine is above my group 6A. This is above, so that takes precedence. So I know my fluorine is -1. So something plus 6 times -1 is equal to 0 because it is a neutral molecular substance. So my sulfur is going to be +6, and my fluorine is going to be -1. And then Cl2, this is elemental, right? That's my diatomic molecular elemental form of chlorine. So my Cl is going to be 0. This is the kind of analysis you have to do every time I want to figure out what's happening in an oxidation reduction sequence. Remember, there are multiple ways I can view oxidation and reduction. For example, oxidation is the process that occurs when the oxidation number of an element increases. That's one way I can tell. Now, if it increases, it's becoming more positive, which means it's losing electrons. If an element loses electrons, that's also oxidation. If a compound adds oxygen, that's also considered oxidation, and I could actually use my oxidation number assignment in order to prove that to you. If a compound loses hydrogen, that's also a sign of oxidation. And then if a half reaction has electrons as products, these half reactions are when I take the entire redox reaction and I isolate the elements that are undergoing oxidation, and then as one reaction, and then I isolate the elements that are undergoing reduction as one reaction. So basically, I'm looking at the oxidation process separately and the reduction process separately. The half reaction for oxidation is always going to have electrons as products. Now, reduction is the process that occurs when the oxidation number is going to decrease. So that means I'm gaining electrons. If I become less positive, I become more negative, and that means I am gaining electrons. The other way to know this is gain electrons. The compound will lose oxygen in reduction. The compound can gain hydrogen in reduction, or the half reaction, which is that second half of this reaction, after I take away the oxidation part, has electrons as reactants. These are all ways that you can keep track of what's happening in a reaction that is a redox reaction. These different rules allows us to assess what's happening. In organic chemistry, for example, I am going to use this add oxygen and or lose hydrogen as a classic sign of oxidation, and the lose oxygen and or gain hydrogen as a classic sign of reduction. A lot of times I'm going to use these other processes, but actually the fundamental process always occurs where oxidation is a loss of electrons and reduction is a gain of electrons. So that's always true, regardless of how you look at this. These other types where I'm looking at oxygen and hydrogen are going to be specific for reactions that include oxygen and hydrogen, and that doesn't cover every redox reaction. Once I determine what's oxidized and what's reduced, I can also figure out these two terms. The oxidizing agent causes oxidation. So to cause the oxidation of something else, it actually has to gain electrons. So this is the species that is actually being reduced. So this is like opposite day. If I am being reduced, I am the oxidizing agent. And then the converse is always true. The reducing agent causes reduction. So it is losing one or more electrons. It is the species that is undergoing oxidation. And that, again, is opposite day. If I am undergoing oxidation, I am the reducing agent. So questions on tests might be something like, here's a reaction. Identify which species is being oxidized and which species is being reduced. Also identify which reagent is the reducing reagent or reducing agent and which reagent is the oxidizing agent. So in order to do that, what you're going to have to do is sort of track your electrons using oxidation numbers or other various things that we just discussed in order to figure out where I have oxidation and where I have reduction. So here, my carbon is elemental carbon. So it has that oxidation state of 0. My sulfur is also elemental. Both of those are elements. So my charge there is also 0. But when I look at CS2, when I look at this chart, I'm going to notice that group 6 is always a -2. It doesn't say anything about carbon here. So when I go down to this piece, to assign the oxidation state of carbon, I'm going to use the fact that in this particular compound, sulfur has a -2 oxidation state. There's 2 sulfurs, so that carbon has to be a +4. So carbon goes from 0 to +4. It's losing electrons. It's increasing its oxidation state. Carbon is oxidized. Carbon is the reducing agent. Sulfur changes from 0 to -2. Sulfur is going to gain electrons. 0 to -2 becomes less positive. It's a decrease in oxidation state. And sulfur is reduced. That sulfur is now the oxidizing agent. So this is also another idea. Here's a reaction. I have iron metal reacting with oxygen gas going to Fe2O3. This is a clear-cut sign of redox because I have an element that is a free element going to an ion. So again, my oxygen or my iron in its elemental form is 0. My oxygen in its elemental form is 0. Here, my iron goes to a -2, and my oxygen goes to a +3. So iron, I'm going to write the half reactions. Iron goes to iron +3 electrons. This is oxidation half reaction. And then O2 goes to 2, O -2. So I'm going to add electrons in order to do that. And what I'm going to see is this is the reduction half reaction. These are the half reactions where I just isolate the reduction and the oxidation part. Now, that means that the oxidizing agent is going to be iron. Nope. The oxidizing agent is going to be oxygen because oxygen is reduced. And the reducing agent is going to be iron because iron is oxidized. So this whole scheme is something similar to what you're going to be seeing on tests and quizzes. Here's another example. I have an ionic compound where my iron is a +3. My oxygen is a -2. But notice my oxygen is a -2 before and after, so that actually doesn't participate in the transfer of electrons. Instead, I have chlorine or carbon, which is elemental 0 state. And then using the fact that my oxygen is a -2, I notice that chlorine or carbon goes from 0 to +4. So it gains electrons, it loses electrons, sorry, so it's oxidized. So this is losing electrons. Iron going from +3 to 0 becomes less positive, right? So it's losing or it's gaining electrons. And that's reduction. So the reducing agent is going to be the species that's oxidized. So this is going to be the carbon. And the oxidizing agent is going to be the species that's reduced. So it's going to be the F2O3. Usually when it says agent, it means reagent. So the species being reduced is the iron atom. The oxidizing agent is actually the Fe2O3, if that makes sense. Combustion reactions are characterized by the reaction of a substance with O2 to form one or more oxygen-containing compounds, and they often include water. Here, I want to track my changes in oxygen and my changes in hydrogen like we talked about before. So we saw before that methane reacts with oxygen to form carbon dioxide and water. Well, if I assign oxidation states, I'm going to notice that hydrogen is a +1, which means there's 4 of them. Oxygen has to be -4. This is elemental oxygen, so it's a 0 charge. And carbon dioxide, the carbon actually goes from a -4 to a +4. So it's losing electrons. It's being oxidized. And then my hydrogen does not change. It's +1 and +1 on both sides of the reaction arrow. But my oxygen is going from 0 to -2. So it's gaining electrons, so this is reduced. What I want to note though, is I have that alternative definition. The carbon is adding oxygen, which means it is oxidation. The oxygen is adding hydrogen, which means it's reduction. This carbon is also losing hydrogen. CH4, the carbon loses the 4 hydrogens and gains the 2 oxygens. By that other definition, this is defining the process of oxidation. When I look at oxygen here, it's adding hydrogen. I can't really say anything about gaining or losing oxygen because oxygen is there, but it is adding hydrogen, which is the definition of reduction in that alternative sense that we just talked about. So let's look at this. Ethanol is the alcohol in alcoholic beverages. Notice that I'm going to use this alternative definition. My carbon is going to be gaining oxygen and losing hydrogen, which is going to be oxidation. And then my O2 is going to be gaining hydrogen, which is reduction. So I can look at this reaction and decide what's happening in my transfer of electrons just by looking at the gain and loss of oxygen and the gain and loss of hydrogen. When I do that, I don't have to go through and assign all these oxidation numbers. I just have to track where my oxygens and my hydrogens are going and where they came from. And then I can do sort of an easier assessment in these particular cases. And this is what you're going to notice if you take organic chemistry as well. Now I could go through this and assign oxidation numbers to every single element and I would get the same result. But it's much easier in this particular substance or example to do it this way, where I'm looking for oxygen being, or oxidation being the gain of oxygen and or the loss of hydrogen, and then reduction being the loss of oxygen and or the gain of hydrogen. So you definitely want to consider those because they'll make your life simpler in certain instances. At this point, I'll stop, and there will be one more lecture, which we talk about the activity series of the elements. And I'm stopping now because this is getting a little lengthy, and I want to, instead of rushing, take my time and explaining what's happening in the next several slides. So I will be back, and I will see you soon.